she would have viruses that would be sent in by customers. Of course, these weren't viruses sent over the internet. We didn't have that. They were on floppy disks in mailers. Okay? And what was interesting was we never, there were no computer viruses ever written on Saturdays, Sundays, and bank holidays. I don't know why. Maybe it's because the US Postal Service wouldn't actually deliver on those days. So I'll tell you one brief story from that time. So again, in the day of not big data, we once received an envelope, floppy mailer from Tibet. We used to get them from all over the world. And there was a note with this floppy disk written in English saying that this disk, no matter what computer you put it in, it would trash the disk drive of the computer. And I said to myself, whoever wrote that is smoking dope, because there's no computer virus that can damage hardware that we know of. And so, of course, what do? I stick it to my computer and see what happens. Well, this didn't work. Obviously, I used a sector editor, I used Norton Utilities. I couldn't find anything on the disk, so I said, okay, maybe something's wrong. I tried another, I tried sticking my disk in again to try another utility, and my other disk wouldn't work. And I said, wow, wait a second. Something's going on here. How could this be? So I tried another disk, that didn't work. I said, okay, this has got to be a fluke. Maybe my drive went bad. So what do? Of course, you're an intern. You take the drive out, you stick another drive, and you stick the original disk in again, because, maybe it'll work. So stuck the Tibetan disk in, the new drive, analyzed it again, tried sticking another disk in, that didn't stop working. I said, holy mackerel, I have a computer virus. I didn't even boot off the disk, and yet it crashed the disk drive. And this is the day again before we did big data. And finally, I just took a look at the disk, and I realized what was going on. It was the honey virus. There was honey on the rim of the floppy disk. Which in fact it was a computer virus of some sort. It would actually infect the drive and infect other disks as well. So that's my first story. Those are the days when we literally can't analyze every virus. There was no big data. Now, about 8 years ago, we realized we had a problem. There were so many computer viruses, malware programs written, that we just couldn't keep up with the threats. Right? They were being released literally 1 per second, 1 per 5 seconds, 1 per minute on some of these websites. And in fact, in the traditional model, we have to get a customer sending in the virus, we have to get it from another vendor to analyze it and then produce a cure. So we weren't even getting these threats because they were micro-distributed. We weren't even seeing them because customers didn't know they had them. Because frankly, there are only 5 of them in the world, and what if all the 5 of those customers don't know they have a threat? And we said, we have to do something different. So we designed something called the Insight System. Barry actually works on that now. Very handy. He can talk about it. And it was a very sort of an interesting idea. We said, hey, wait a second. We have hundreds of millions of customers. Can we somehow leverage their wisdom and ignorance to identify computer threats, computer viruses for us? In other words, let be the eyes and ears. Much like, for instance, Amazon uses their customers for books. So how does it work, or how did it work? Okay, we had a theory that basically we can measure the hygiene of every computer on the internet. Okay, your computer. How often do they get infected by threats? You might be very unhygienic, or maybe a teenage son at home who's very unhygienic, or a young boy or girl who's getting into all kinds of trouble, downloading cracks, using pornography sites, maybe getting infected all the time. Okay? On the other hand, you might be very hygienic. Your computer rarely gets infected, which is not to say you don't introduce new software. You do, but you're very careful about the software that you introduce, and so you're very hygienic. Now imagine I have a new file on the internet, and I collect all this hygiene information, and I also collect adoption information on files anonymously. So I know any type of file is adopted by you. I don't know your name, I don't know who you are, I don't care, but I know you just adopted this file, you adopted the same file, you adopted this file as well, and so on. If I look at the hygiene of this group of adopters, and I find they're mostly hygienic people, that says this is actually probably a safe file. On the other hand, if I have another file, this stuff that is primarily for hygiene, that would indicate that file is likely to be bad. Okay? And so by leveraging the anonymous adoption pattern, the wisdom and ignorance of hundreds of millions of people, we were able to identify which software is good and bad with very high probability. In other words, the spectrum of reputation rating. And that's actually a big part of our security software today. We use reputations derived based on the wisdom and ignorance of the crowd in this way to protect customers. But today, this is really an ingredient. It's an ingredient in our software. And I'll tell you actually one little story about that, and then I'll go, I know I'm almost done here. But It was an interesting time when we were developing the system because we were just learning how to use big data. We had bugs in our system, and in fact, we had one bug in particular which was interesting. We discovered that we were actually blocking software, not with just a bad rating, but software with no rating at all, accidentally. Our product actually had a bug, and we said, the product said, if there was no rating for the software, we'll simply block it. Guess what? Nobody actually reported that to us. It was not reported as a bug, because most of the software that was unknown to our customers was software that was bad. By blocking unknown software, we had so much information about the landscape of software around the world that we could actually say that if we didn't know about something, it was almost certainly bad. It didn't come from a trusted website. Okay? So it just shows you the power of big data. Okay? If you have lots of information, you can actually find all kinds of interesting insights that you would never expect. So that's our insight system, and we use that today, and we started about 8 years ago. But where are we going as a company, and why do I talk about sort of this progression? Symantec now has a new strategy, and that strategy is something we call sort of internally unified security. That's the working title. Symantec used to be a point product company. We used to produce products like our Nordic products, and Symantec protection and data center security, and DLP software, and so on. But we're transitioning from being a point product company to a security intelligence company. Okay? What do I mean by that? We see the power of big data in helping to solve security problems. Okay? Specifically, we have security products everywhere around the world, on every endpoint, on gateways, on email servers. We monitor more email traffic than anywhere else in the world. We monitor more endpoints than anywhere else in the world, and so on. Okay? So what if we were to take those products and instead of just blocking threats and doing what we normally do, if a customer is willing to operate, we turn those into rich sensors, rich sources of intelligence. So that in addition to blocking threats, they also say, hey, I saw a new file adopted, I saw a logging database, I saw a network, I saw a setting change. Almost like putting digital video cameras, anonymous digital video cameras on every choke point where we sit. And then taking that intelligence, ingesting it into a big data system, and analyzing it to serve many, many purposes. That's our strategy going forward. Leverage our massive customer base who often gather rich intelligence and then use that to identify tenants. So what can you do with that? You can identify that you, for instance, I don't know who you are, but you access documents at a certain rate. You don't read documents on weekends. You don't read them, or maybe you read them from a certain geolocation all the time. Okay? Maybe you only read a certain subset of documents over time, but you don't read these old documents you created earlier. What if I see a change in that pattern and say, oh, wait a second, there's an anomaly. Maybe there's a key in your machine, or maybe somebody's misusing your device, or maybe you've gone rogue. That's just one use case. I guess what I'm trying to point out is that we see so much power in big data with the biggest civilian intelligence repository for security intelligence in the world. And so over the coming year, I think what you'll see, interesting, is we will be adopting our products more and more for customers who are willing to work with us, and it's not going to be for everybody, to collect more of this intelligence and then develop a rich big data application on this intelligence in order to provide more value to customers. Whether it be augmenting existing security products or actually developing entirely new offerings based on the intelligence itself. So I guess what I'm saying is that we really think big data is a big thing. And we are transitioning from a company that really uses big data as an ingredient to a company that's basically basing its products and services on that intelligence. So I welcome all of you, and I hope you have a wonderful meeting. And I don't know how you want to raffle this off, but if anybody's interested, it's a techno thriller, cybersecurity thriller, out on April 14th called The Florentine Deception. I'm donating all proceeds to charity. So buy a copy, enjoy it. And feel free to give it out at the end. Okay? I'm going to take off now.
Thanks for the great presentation on data. So just a few quick announcements. As I mentioned, for the last few years, we have taken action on as well as big data day is on June 27th. For announcements for speakers, sponsors are nicely followed. We're almost done with the finalizing completion, but again, it's going to be June 27th for tracks, Spark, SQL data science, and big data tutorials. So we look forward to the email community all the time. Do this registration for that event. It's going to be completely free. So have a lot of it is pretty good. We have next we have in a few weeks. That's going to be a Saturday as well. Robert is actually really great topic on Spark jobs and everything. So they are leaders in Spark and it's like our Spark jobs are sharing. That many videos are speaking for today. It's Jon Haddad. He's a technical advisor in Datastax, and he's going to have a great presentation on using data Spark Cassandra together. So thanks to our host Samantha, and thank you John for coming today. Thanks for coming.
Hello? Can everyone hear me? I don't know, is this working? No, you can't hear me?
I can hear you.
You can hear me? How about now? How about I just speak really loudly? Will that work? Okay, amazing. Before I get started, I'm just curious, who here has used Cassandra before? Do we have any veterans? Nice, hands, I love it. Anyone using Spark? Okay, great. We have some Spark users, some Cassandra users. How many here are still using relational databases? Some active. All right, a ton of hands. Okay, great. Then I have brought the exact right set of slides. What I want to talk about first is kind of the evolution of data. How did we get to the point where we need a tool like Spark? And Cassandra. The first thing that we want to take a look at is small data. So what is this? This is a data set that we can fit on our laptop. We have no problem. It's a few hundred megs, maybe it's some log files that we want to look through. And we want to process them. And to process it, we use, let's say, our Linux tools that are on our laptop. We use sed, awk. Maybe we write Python or Ruby or even Go nowadays. And we can just crunch that file and get some result, and it's totally fine. We can give the results to somebody. This might even be a CSV or Excel. It's just, the only requirement is that it's on your laptop and it's not a multi-user system. So, what are the limitations here? The big problem is that we can't really do anything concurrent, right? We've got one user using this file. We just can't really do anything. So we want to step up, right? Now we want to step into the world of medium data. And medium data is where we bring out our relational database. Okay? This is where we take MySQL or Postgres or SQL Server, Oracle, tools like this. And they're really convenient for a lot of things. And it's especially convenient if your data fits on one machine, right? And this is now a big database server with a bunch of drives, or maybe you decided to use it. That's okay, I'm not a big SAN fan. So in the traditional world, we see a lot of this with web apps, okay? So I've built plenty of sites that run on one database server. Maybe they've got some replicas in place, but effectively you're dealing with a data set that's sitting on one machine. And this is cool. You can have hundreds of concurrent users accessing the data. And it works fairly well for a certain, for a certain point. And there's some nice things that you get with this. You can get assets, you have transactions, you can do things like triggers and store procedures, and everything feels really smooth, right? It's easy to work with. One of the big problems though with this is it scales vertically. So I mentioned SAN, it's expensive, right? You want to put everything on a SAN, you're going to spend money. You want to get a bigger computer, you have to buy a whole new machine, and now your old one, what do you do with it? Today, I don't know. It's expensive to continuously replace the hardware. And it definitely gets more, like as the hardware gets better, it gets way more expensive. It doesn't scale linearly at all. So the question is, how do we, can we use the relational database for big data? So let's take a look at some of the limitations that we see along the way. First thing that we start to notice is that ACID is actually a lot. With a database like MySQL or Postgres, you're going to be using asynchronous replication, right? So let's start out. We have our master, all right? And the next thing that we're going to do is we're going to introduce our client. And this guy is going ahead, he's talking with the master, and he's doing some queries, and everything's nice and ACID, and we're very comfortable with this. But when we decide that we want to add replication, now all of a sudden we have to deal with the fact that we have replication lag. Replication lag is problematic because if you write it to your master and then you go ahead and query your slave, there's a chance that you're going to get old data back. You're no longer wrapped up in this nice cocoon of consistency. As a result, we don't have consistent results. The next thing that we see is that third normal form doesn't scale. We have these crazy queries that I used to be proud to write things like this. I was like, oh my God, I have this 62-line SQL query and it's some ridiculous report and it takes an hour and a half to run. This starts off as a source of pride and it turns into a source of pain. It's very problematic. You really don't want to be doing this in production. I mean, we have a ton of problems here. You start running this, you're still using spinning disks, now you're paying overhead of seats, right? Your data doesn't fit in memory. This kind of thing doesn't really work very well. And you definitely can't expose this to something where you have an SLA. Like if you're saying, I want a response in 10 milliseconds or less, there's no way that you're ever going to be able to do this in production. It's ridiculous. So the next thing that we noticed is we try to shard, right? And that's when I decide I'm going to split my data across my machine. I'm going to have maybe a messaging system, a user system, something for photos. And the problem here is that we can no longer do joins very easily, right? Before we could say, I want to join users and messages. That was really convenient. I get one result back, and it's a bunch of data. But once you split your data across multiple shards, you can't do that. So the next thing that you realize that you lose is your aggregation. Okay? Because as you continue to shard, you might not say, I'm going to keep all my users in one system. You might say, my users are going to be split across 10 shards. You can't really do aggregations across that. So what you end up doing is you denormalize. You copy some of your user data over your message system, then you copy some keys around, maybe you copy your username or your email addresses to all the different tables to avoid having to do all these complicated lookups. You also run into a problem where if you want to use secondary indexes, and you have a whole bunch of shards over here, you have to query all of them at once in order to get the result of the query that goes across shards. So this is that example where I said my user system is now spread across 10 machines, 10 shards. And I said, I want to do a search for users that match, let's say, the state of California. Well, I have to hit all of these shards. It's very inefficient to do this because the number of queries that you can do will not change no matter how many machines you have. If you have 10 times the number of machines, you're still going to be doing 1,000 queries per second per machine. So this doesn't scale very well. So you end up with all sorts of problems there. Adding shards requires manually rebalancing. So this is a huge pain. I don't know if any of you have tried to do this. You end up writing a ton of application code to manage moving data around your cluster. It's just kind of a nightmare. You don't want to do that. It's a pain for people in operation, it's a pain for development. You just have a lot of things that you have to think about. And then if you want to do any schema changes and you're dealing with a whole bunch of shards, you have to make sure that they're applying to every one of the nodes or every one of the shards. It can be, again, problematic and kind of weird. And you end up looking like this guy. The next thing that we find is that high availability is very, very difficult or impossible. So let's take the situation where we have, let's say, our master-slave situation. When a master fails, who's responsible for handling the transfer of the responsibility of being the master? Do we have some other process that's sitting there watching? Who watches that process? We have just a lot of moving parts that make it complex and hard to deal with these failures. And as a result, if any one of the pieces along this mousetrap fail, you end up with a situation where you have downtime. And downtime is actually pretty frequent. Something else I'm going to talk about. So we need to take down this master, slave, some of these machines all the time. If we want to do OS updates, security updates, upgrade the database software, we want to change the settings. Let's say we want to do an optimization. For the MySQL world, we want to change our DB buffer pool size. Or we want to put more RAM in the machine. These are things that we have to deal with. So there is downtime that does happen. Can you reliably have high availability despite the fact that your losses are down? And the other one on this last on the list here is, are you able to do multi-DC? And this is extremely hard. If you want to do multi-DC with something that replicates one way asynchronously. You can do master with MySQL, but trying to do that across data centers, it's just going to fail. So what have we learned here? We see that scaling is a pain. We see that it's pretty naive to think that you can do ACID in the big data world. We're talking dozens, hundreds of machines. This isn't one machine, it works, that's fine. Dozens of machines, ACID fails. When we have to reshard, we have to move around our data. it's a huge pain, right? Like, we don't want to have to do this. We're gonna have to denormalize, right? I talked about copying keys around, copying your data around. It's the only way that you can achieve good performance with these systems. You're not gonna be joining anymore. You're not gonna be doing wild aggregations. You wanna pre-compute this stuff and reference the pre-computed information. High availability, as I said, huge pain trying to manage this. And the other thing that's important here is that the more servers you add to these systems, it generally increases the amount of work. So when you go from 10 machines to 20 machines, you're doing almost double the work to try and manage this cluster. You have to hire more people. You can't take that same team of 2 dudes or ladies and roll this thing out and increase the size of your cluster and have it be effortless. So what if we were to take all these problems and kind of look at the world and say, what if we were to design a database from scratch? What if we were to put some rules in place and we were to make some concessions? What would we end up with? The first thing that we know is that consistency isn't practical, right? We're not going to do it across hundreds of nodes. So we just say, you know, we'll just be eventually consistent. We'll use asynchronous replication, and the developers will be aware of that, and that's okay. We know that manual sharding and rebalancing is really hard, okay? So we're going to build it in. Let's make sure that our system, if we have 100 nodes in this cluster, it just does it for us. I should be able to add a new server, and it should just join the cluster, and that's okay. And it will then go ahead and start serving requests. And it should be really easy to do that, right? I shouldn't have to do a lot of work. I shouldn't have to roll out massive changes to configuration files. I shouldn't have to tell 32 people, and they shouldn't have to push source code that points to the new IP of the new machine and be ready for this huge migration, which is crazy. Another thing that we know is that every moving part that we have makes the system more complex. There's more stuff that exists, we need more redundancy, and there's more chance of failure. And the failure scenarios are more complex. So ideally, we have a system where there's no master slave, there's just a bunch of machines. Okay, so we get rid of this whole idea of a machine is special. It's just a bunch of machines that are all the same. The other thing that we talked about earlier is scaling up is expensive. We don't want to have to say, buy a $100,000 piece of hardware, $200,000, and then just keep going bigger and bigger and bigger, add on the sand. Like, let's put in terabytes of memory into one machine and hope the power doesn't go out. This doesn't work very well. So what we want to do is we want to buy commodity hardware, right? We only want to spend a couple grand per machine, and when we need more capacity, we just go ahead and add more machines. We can take a 10-node cluster and turn it into a 20-node cluster, and it should get double the reads and writes. So our throughput will double as our cluster doubles. And then the other thing that we have here is we saw what happens when I do a query and it hits secondary indexes and I have to hit all of these nodes. Well, that doesn't scale well either, right? So one of the things that we're going to say is we're going to denormalize for real-time query performance. We're going to make sure that we're only hitting one server for every query that we do. So that kind of leads us into, there we go. That leads us into Cassandra, all right? So Cassandra is a fast distributed database, and it's built to solve all of the problems that I've already outlined. We get high availability and linear scalability. So that means that this system is always on. This is something that Cassandra is famous for. You can have rack failure, you can have total data center failure, and you can still have a working application. Linear scalability, as I mentioned, means that we can double the size of our cluster. We double our throughput, both reads and writes. We have predictable performance. So as I talk a little bit about denormalizing your data and the way data is stored on disk, you'll start to see why Cassandra is very predictable. We don't want to have 1 millisecond on one query and then 100 milliseconds on another query. And we don't want different users to experience different latencies. That's not good. We want a consistent profile for everybody that uses our system, no matter how big they are. We don't want single points. Well, Cassandra doesn't have a single point. Every node in the cluster is the same. There's no master slave. We can go multi-DC. We can run these things across 6 data centers if we want. We can survive. If the US just ceases to exist, we can have our Europe data center still run. I mean, we might all be dead, but the data center will live on, and our Cassandra cluster will be okay. We do want to put this on commodity hardware, right? We don't want to spend 200 grand per box, and we want it to be easy to manage operationally. Now, one thing that I want to mention here is that this is not a drop-in replacement for relational databases. This isn't the type of thing where you're just going to go, you know, I'm going to port everything over, and I'm just going to say, this table exists over here, so it exists over here, one-to-one. I don't have to think about anything. Turn it on, magic everywhere. We're going to take a little bit of a look at CQL. It's like SQL. It's how we create our tables. It's how we talk to the database. It looks a lot like SQL, but it does not exactly work the same way. So it's a familiar construct, but don't make assumptions about the way Cassandra works until kind of we go through this. Before we go any further, anyone have any questions? I love questions. Yes.
Kind of a side question. So the change of the requirements of the data story line up previous as hardware, we see the hardware manufacturers have changed.
Have they changed?
Yeah.
Well, the thing is that hardware manufacturers have always offered, come on, let's say, one-use servers. HP is offering the Moonshot. Like there's lots of really good options that aren't super expensive. You don't have to say, hey, I need a SAM. You can just use standard racks, one-use servers, everything looks great. And those aren't terribly expensive. $5 grand.
So I'm not very familiar with deploying RDBMS on a very large scale, but whatever you said seems to imply that in a master slave situation, you can't just query a master and it will automatically figure out how to join across different servers. You have to actually manually manipulate the whole thing and rewrite it. Is that correct?
The question is, when you start to scale out with your shards and you go into that sharding process, can you just query one master and have it just go ahead and figure everything out? There may be databases that do that. For instance, FullDB, you can query across a whole bunch of servers. But the problem is that doing it predictably at scale, it does not work very well.
So MySQL does not support it.
Not that I know of.
I see. So you have to rewrite all your queries.
So you end up, yeah, exactly. You end up rewriting your queries, and you end up rewriting your entire application. You start out with an application that has, as I mentioned, the cocoon of consistency. You feel good because everything is just so easy to use. It's atomic. Every operation that you do is isolated. But as your application gets bigger, you end up giving up all this stuff. But you don't really get anything back. You're still tied to this old, broken system that made a whole bunch of assumptions earlier, but you still have all the baggage, and you don't get any of the fun.
So I have a Ruby on Rails app, and I decide, okay, I want to have a big data center backend, and I can't just do that.
Correct. If your Rails app just gets huge, you are going to have to rewrite most of it in order to continue using a relational database. And you'll have to rewrite every one of your queries, and you'll have to do all the steps that I outlined along the way.
Thank you.
Would you like to explain your graph?
Sure. The question was, can I explain the graph? So this is a graph. Netflix did a study a few years ago showing the performance of the Cassandra cluster as you added nodes. And what they discovered was that it scales almost perfectly linearly. So as you double the size of the cluster, it will in fact double the performance, both reads and writes. Any other questions? I love questions.
You said that you double the nodes. Is that right?
Yes.
You're going to double the performance.
Right. We go from a 50 over here.
You mean it takes longer?
No, we double the capacity of the cluster. So if we could do 100,000 queries a second with n number of nodes, n times 2, we can do 200,000 queries per second.
Okay, I thought that's what you're saying.
Yeah.
Okay, so this is
Yeah, performance doesn't degrade as you add more nodes. I would just go home if
the
that was
number
the
of
case.
queries per second. Oh, so there's a number of queries you can do versus the number of nodes.
Exactly.
All right.
Yep. Add nodes, get more queries. More questions? No? All right. You're going to have more, though.
So how does that work?
What was that?
Maybe you explain that later, but how does that work?
How does it work? Well, yeah, I love when people ask a question where the next slide is. I can just lead into it. The way it works is because Cassandra is a masterless peer-to-peer system. Think about BitTorrent. Think about how data is distributed. You don't necessarily have to have all the data, but you have a fully, like you have a cluster and there's hundreds of people that are participating in this thing. It's a very similar situation. You don't have, as opposed to downloading everything from one website. So I'm not just getting my Ubuntu installation from the Ubuntu website. I'm just getting the torrent, and a bunch of people can give it to me. The difference here is that when you have a peer-to-peer system like BitTorrent, everybody has a full copy of it. And in a Cassandra cluster, data is going to be spread around the cluster. All right, there's going to be data will be distributed automatically for you. As you add new nodes into your cluster, that's okay. It'll just go ahead and figure out what data should be on there. It'll move it around for you, and whenever you query it, you'll get an answer now. You don't have to think about, as a developer, how big is my cluster? What is going on here? Like, are we in migration? This is not your problem anymore. It just does everything for you. Now, the other thing that we have here is that data is also replicated. So you can tell Cassandra, I have 3 racks, and I want to put only one copy of each piece of data that I have in each rack. That means I can now tolerate full rack failure. The switch goes down, power goes down. That's totally fine. We can do this across data centers. We can have 3 data centers around the world. We can say in each data center I want 3 copies of my data. A bomb can go off, and you'll still have a fully working cluster. I hope that doesn't happen. When you talk to Cassandra, it doesn't matter which node that you talk to, because query is going to be routed to the right node for you automatically. So I can connect to anything, and it will go ahead and get me the result that I need. It will go ahead and talk to all the other nodes, or whichever node is responsible for that data, get me my result. The other thing that you get to do is you can tune your consistency. So you have a couple options here. When you write to Cassandra, let's say that I chose to have 3 copies of whatever data I have. I write to Cassandra, and I will say, you know what? I want you to return when all 3 copies have been written. That's this consistency all. You don't want to use that. It's not very good. It means it's the slowest one, and if you have any nodes down, then there's a chance that this query will fail. So you don't want to do that. What you want to do is you want to say, you know what? I'm okay. If one node acknowledges the right, just go ahead and return okay. And everything else can be replicated asynchronously. So in a second or 2, everything will be done. You just don't have to wait for it. And if one of these nodes happens to go down, when it comes back up, it'll get a copy of the data. It'll take care of it for you automatically. So it's not like, hey, the slave went down. Well, what was the position in the replication log? Like, do I need to think about this? Do I need a DBA to figure this out? You don't. You just bring it back up. It does everything for you automatically. Does anyone not believe me? Sounds pretty cool, huh? That's how it works. Are there any questions?
Yeah. Go. Sure. Yeah, you said if you're in the middle of it and you're only looking for the one, right? So you're fine with that node, but then you have a power failure. Okay, so the data's lost, isn't it?
So if you do a write at 1 and there's power failure, the answer is it depends. So this is where, well, it depends. So if you were writing at 1, it was the only node that was up for some reason, and then you had a power failure, yes, you would lose that particular piece of data. Now, ideally, you don't have 2/3 of your cluster gone and then lose the remaining 1/3 of your cluster because you're kind of in you get a bigger issue there. If the information is sensitive, then you can write at what's called quorum, which means it will only return when a majority of your nodes, in this case 2 out of 3, have returned success. So this is a safer way to do it. It depends on your application. If you're reading, let's say you write an analytics system, and you've got a ton of data coming in, hundreds of thousands of requests coming in, you're better off just giving an answer right away, because the cost of losing that piece of information isn't that much. I lose, I've got a website, I've got 1 million hits a day or 1 billion hits a day or something. I lose one little thing, it might not matter.
But are you saying even if it was written successfully to that one node, wouldn't they just replicate the other?
So the question, unfortunately, is one of my many it depends types thing. When you say you lose a node, I think catch fire. Okay, so if the node were to write the data, like if you were to write it to one, and then there's also a network failure and it can't talk to the other two nodes, and then the power goes out and it comes back on, it will have that data on disk locally, and then it will replicate over to the other nodes. So it's pretty safe. I can come up with some edge cases in which it won't work, but it's pretty intense. And you do have the power to control that.
I don't know if this is within the scope of your presentation, but when the node goes down and comes back up, how does it know whether its data is not corrupt or
How does it know whether it's not corrupt?
And also whether it's not outdated.
Whether it's not outdated. That's a complicated question. I will answer it in 1 minute or less. It knows the data is not corrupt because everything is checksummed, and it knows that it's not outdated because as soon as it comes back up, it's going to receive any mutations that it missed from the other nodes. So it goes, hey, I'm back, and they go, hey man, you missed some stuff. I get to. I think good question. Yeah.
It's actually goes back to the regular scaling that you showed. It's a number limit to this. I'm sure, I mean, physically speaking, it has to be.
There, yeah, so I know of clusters that are over 1,000 nodes. They're being run by Apple. And that's the largest cluster that we know of that exists right now. And I think it's not a technical limit at that point. It's more of a practical limit of managing a 1,000 node cluster from an operations point of view, upgrading that type of thing. Actually, upgrading is probably the biggest operational challenge once you have a 1,000 node cluster. But you can put petabytes of information in that. So what they've done is they just run a couple hundred clusters or something like that. I think they said they run 75,000 nodes in production.
But it's still helpful.
Oh yeah. All right. Yes.
How hard or easy is it to configure this?
Incredibly easy. It's shockingly easy, actually. If you have a bunch of machines at Amazon, you just need to know their IPs to get the cluster started. And then when you want to add a new server to the cluster, you just fire it up. You tell it about one of the existing machines in the cluster. It will talk to them, find out the full topology. It will get data for itself, and it will even tell the drivers about itself. And then, the rest of the cluster will tell the drivers about itself. The drivers will connect to it, and it will just start to work. You don't have to restart your application. You don't have to restart anything. You just, I wrote a fully automated system to manage all this. I had a one-line shell script that was, I had a one-line command that I would run that just had some Python in it that connected to Amazon, booted an instance, installed Cassandra, put a config file in place, started it up, and it would join the cluster, and we'd get more throughput.
So how big does that config for you?
Well, you only have to put in three machines that exist. It will find out about the entire cluster for you automatically.
So like not making big config files like Apache.
0 to 8, exactly. You could grow a cluster from 10 to 500 nodes without changing a config file. And we tried this. This is what we did. We scaled this up to 50, 60 nodes. Not a problem. It does everything for you from an operational perspective. And then when the machine is ready, the drivers, it's a bidirectional communication. So the server will notify the client that there's a new node in the cluster, and they'll automatically start taking advantage of it.
If you don't want to post your data on the third-party server, how much would be the hardware cost associated?
The hardware costs if you didn't want to use a third-party service. It depends what you put it on. I mean, generally, I say $5,000 per server, and you're good to go. And if you put solid-state drives that are really one, you'll get way better performance because they're just amazing. I'm going to move on because I'm not sure what am I doing on time. I'm probably way behind. I always fall behind. So the data structures that we have starting here look a lot like the relational side of things. I warned everybody, I hope you still remember. The top level, we have a key space. This is similar to a schema in our relational database. And then the next thing we have is a table. Okay? Same idea, table stores a whole bunch of information, and that table has structure. It's going to have columns, and those columns have types. Within a table, we have a partition. And this is a little bit different than what we're used to in the relational world. A partition is a grouping of rows. And this is really, really useful if you have a bunch of data that's related. Like if we have the classic example of Cassandra's time series, right? So if we got sensor data, say a manufacturing line, GPS off your phone, just something that's coming in, and it's data that you have to read that's in a timeline, and traditionally it's immutable. This is where partition is really useful because I can do one query, and all that data is going to be sitting together. It's going to be stored sequentially as well. So this sensor data is coming in, and it's just being stored one after the other. And then I want to go query it. I say, you know what? I need less than 50,000 sensor readers. This would be crazy in our relational database. This just does not work very well. It's going to hit some secondary index. It's going to perform really poorly. Even ingesting this data in the relational world is a nightmare because it's trying to wrap everything in atomicity and isolation. So you end up with this transactional overhead. It works really, really well in Cassandra. So within a partition, we have something called a partition key. Partition key is going to determine where in the ring that data lives. Okay, and so basically, you take that partition key, you apply a hash to it, and it points to a server, and you go, okay, you're the first replica. And then we use our logic to determine the other replicas that are in there. It does this for you automatically. The logic I'm referring to is when we say, don't put 2 copies in one rack, right? We don't want rack failure to take down our application. Then we have clustering keys. In the case I just gave of sensor data, we're going to say our clustering keys are timestamp. Okay? And as that data comes in, it's going to be sorted in order of that timestamp. So it's really fast to query, and you can store a ton of data that way. So we've got 2 options here. We can have one row in a partition. This is where we don't declare clustering. So this might be just our user system, all right? And in here we've got me. I'm John. I'm 33. I don't know if any of you do that. And I'm an evangelist. And then we have Luke. Now this Luke actually. And we've got 20 people in here. And to create this table, this is actually probably going to look really familiar. I mean, a lot of people raise their hand for relational. You should know this syntax. And if you want to select data out of here, you're going to use this. So this should be pretty easy. If you want to get started with this, you can probably just guess what to type in here, and you're going to get a table, and you're going to be able to select data. Now this is where the clustering key comes in. This is where that partitioning comes in. I don't want to talk about what I was talking about. So in this system, we have comments on photos, right? And this is pretty common, right? Any content system, YouTube, whatever, we've got comments. And we know that we're always going to say, I want comments by a particular photo ID. So I want these comments to be stored together. That way, when I do a query and I say, I want all the comments for a photo, I only have to talk to one server. And even if we had 50,000 comments, they're all being stored sequentially in the order that they were written. This is the beauty of the system. And so here I'm using integers, but we're actually not going to use integers in real life because they don't perform very well when you're trying to do distributed counters. So we're going to use UUIDs. So we're going to have photo ID, be UUID. And then our comment ID will actually be something special called a time UUID, which is, I don't know if you guys have done any Python work or actually any language. It's a UUID 1. Includes a timestamp as part of the specification when the timestamp was generated, and the information will be stored according to that timestamp. So basically what we have here are 4 rows, and they're spread across 2 partitions. So it's going to look like, oops, it's going to be sorted, like I said, sequentially on this. And the thing that you're going to want to keep, the thing that's really important to take out of this is you want to embrace denormalization to do as few queries as possible across your cluster. Your cluster is not going to scale very well if you say, for this one API call, I need to do 500 queries. You're going to want to take that data, you're going to want to copy it around a whole bunch of times. For the same way that we said, we don't want to have to query secondary indexes across 5 machines. We don't want to have to query 100 machines or 200 machines in order to satisfy one answer. So we embrace denormalization, copy data, copy our usernames around, we copy our photo IDs, and all the things that we need in order to answer questions. And what we have here, we have our partition key. We have a partition key. we've got our clustering key, and it's good. So the thing that we're going to remember here is we model tables to answer queries. And this is why I said don't just assume that you can take your relational world and bring it over to the Cassandra world. This isn't their normal form. It doesn't work that way. We start from the opposite. We say, first, what do I want to ask my database? And we're going to store it that way. We're going to store it in a way that it's efficient to retrieve. This is what gives us predictable performance. We can't just say join 26 tables together. No, it's how long that'll take. We say I want to get an answer from one server, and I want it to do as few disk seats as possible. That's how you get predictable performance. Before I move on from this, there have to be questions. Yes, you then you.
So I think you hinted at it, but it was not. I don't know if I got it affirmative. You can partition data in two different ways within the same database, correct?
One way. When you create a partition, you effectively say, I want this photo ID to be my partition key. This comment ID over here becomes my clustering key. And that's one table, and it's stored one way.
So,
and, I'm sorry, go ahead.
well, I think I understood that. So that I was actually hoping there would be more than one way to partition this thing, because that I can see easily, like, you know, application like Facebook or something, where you, in some certain situations, you want to get all the comments belonging to a photo, or all the comments belonging to a user.
So the question effectively is, I want to be able to query my data multiple ways. How do I do that? The answer is, you're going to store your data a whole bunch of different ways. So for that, you might say, let's take this example here. This is my user table, and I want to ask the question, who here, I want all the people that are 33 years old. I'm actually going to create another table to answer that question. Instead of creating secondary indexes, you're just going to denormalize. You're going to write your data 3, 4, 5 different ways. So in this case, I would create 2 tables. In your example, his example question was, I have photos with comments. What happens if I want to select comments by a user? You would have 2 tables. One would have the organization that we had over here, and another table would have the user ID as the partition key and the comment ID as the clustering key. And you store your data 2 different ways. And no, there is no way for it to manage it for you automatically.
They're not automatically synchronized.
Correct, they're not automatically synchronized.
So as your app evolves, you have to write more, make sure that wherever you're updating your data, you are updating it in 2 different tables at the same time. And so on.
Yeah, the question is, what happens when your app requirements change effectively? Yes, you have to go through the process of looking through and making sure that you're covering all your bases. Now, Cassandra's traditional best workload is when you're dealing with immutable data. So I use these because these are really easy to understand, and you can go ahead and do this, but the workload that you're going to see more frequently are things like time series, or I know this doesn't, it's maybe a little surprising, but you would see this more as well in a bank environment, because banks don't actually update information, they just have immutable ledgers. So basically, while you can do this type of system and you can like update things, it works much better when you've got 3 or 4 copies of your data and you're not going back and updating, because the exact problem that you are asking about, what happens when I want to update 26 different spots. You can imagine. Yes.
So I have 2 questions. One is it fair to say that Cassandra doesn't support joins? Because it doesn't be.
It is correct.
All right, okay.
I even have a slide that says no joins.
Okay, well, that's fine. Okay. And the second part is, if the data is not time series, right, then Cassandra might not be the optimal way to show. I mean, there are a lot of cases where you don't have time series.
Yeah, there are a ton of cases where you have time series. I would say this, there are certainly a whole bunch of use cases where Cassandra is not the right fit. I would not say, if I were to make a Venn diagram, I wouldn't say time series, yes, Cassandra, not time series, no Cassandra, because there's a ton of use cases that exist outside of time series. I'm just saying that's like the sweet spot. It's like a perfect scenario, it's time series.
The time series is very good.
Yes.
It's okay.
is a bad partition key, but it's a great clustering key. It's a clustering key is only used for sorting of multiple rows within a single partition. It would not be wrong. But as the caveat to that is, I would always recommend using a DUID, one-time UID, as a clustering key instead of timestamp, because it's more flexible. All right.
Yeah, so for ACID types of transactions, you never use the same.
So, if you need ACID at a very small, like a small part of your application, you do have an option called lightweight transactions. But I don't think I go into one here, but it uses a consensus algorithm called Paxos, and it'll basically come to an agreement, and you can do not the full spectrum of like an ACID transaction where you're like rolling 26 statements in one thing, but at a per table level, you can get that type of isolation, but you do develop performance by doing that. So if you were thinking like the example that I hear frequently is like I have a concert venue and I need to make sure I don't double sell the seat, you might use it there. But other than that, there are usually creative ways to do your data models.
But for like critical transactional systems that are like, you know, the structure goes bad, like somebody gets sued or something goes to jail, you would use Cassandra for that.
I'm going to stick, the question was, if I really needed, would use Cassandra for that? My answer is, it depends, because there are a million ways to model your data around it that everybody is doing right now. If you have an example, I'd love to talk about that. Yeah.
The only reason I ask is, kind of like the standard paper that Google wrote out, where there's lots of kind of talk about implementing something that has geographic consistency and across data center application like Cassandra, but also can support ACID transactions and arbitrary sort of key values.
So the problem with that, I would need to reread the paper, but my assumption off of that would be that there would be limitations around. It's not optimized for the right system, is it?
It's pretty fairly close. Foundation can be close to that. Some loads there, but I think it's kind of separate.
Yeah,
Separate use case for transaction heavy applications.
I think we'll take that off.
Yeah, but I think your point about immutable data being a really good for Cassandra makes a lot of sense.
So, John, on about ACID, we had a really good discussion almost a year ago with Cassandra.
Yep.
And the conclusion was, you actually don't need it in most circumstances. So even like the banking stuff, the eventual consistency works. Even in the stock market, the eventual consistency works. So there's a few cases like that. See, you only saw that once one person. We actually need it.
Yeah, it's very rare. Most, and that's a great point. Banks are the most eventually consistent system on the planet. And it's funny because everybody thinks that, oh, what happens? You have to update your bank balance. What happens? Guess what? Like if you write a check, your bank balance doesn't update for days. You pull money out of the ATM on the weekend. Who knows what's going to happen? Especially if you do it in a foreign country. Like these systems are all ledger-based, right? And ledgers are immutable time series data. So something comes in, you update your ledger, maybe you put some aggregations in place in order as an optimization. But in the banking world, there are no update this cell with a new balance. It doesn't work that way. And I know this because one of the guys on my team worked at 2 banks and confirmed it. So it's definitely on. Exactly. Yeah. You do not ever change the past when it comes to bookkeeping. You gotta.
Yeah, one quick one. That's Cassandra support aggregation. You mentioned about aggregation.
No, I agree.
Oh, yeah.
That's actually going to be in the slide that says no joints. So I think you might be cheating.
So, correct, and so you say there's 4 rows to partitions or color coded because of
Exactly. Yep. I color coded the partitions. I could probably do it better. Sorry. All right, I'm going to move on because we're going to run out of time. So we talked about embracing denormalization. We talked about this and running your slide right here. We have no aggregations. We have no joins. The only thing that we're going to do is, in general, we're going to select by our partition key. We're not going to say, hey, Cassandra, just give me this piece of information that satisfies these arbitrary requirements, because that means that we're going to have to talk to the entire cluster. Performance is terrible. We don't want to do that, right? That's what we learned in our earlier slide. We're going to have to manage our own secondary indexes to answer your question. You have to do it yourself. It's kind of it's a little bit more work when you start writing your app, because you have to think about these things ahead of time. But the result is you have an application that scales really, really well. Unfortunately, there's no magic bullet. You can't just say, hey, give me 1,000 node cluster that does everything for me, and I can just like throw arbitrary queries out, and that's not something that exists in this world yet. But that's why we get paid. So it's not a bad thing. But you know what? A lot of people are sad about that. We get upset to say, you know what about all the ad hoc stuff? What happens if I don't know all my queries in advance, right? And guess what? We had an answer to that. It's very exciting. Apache Spark finally gets to bust into this part of my conversation. So Apache Spark works really well with Cassandra. Like, we are so ridiculously pumped about this because it fills the need for everything Cassandra doesn't do out of the box. So you can do batch processing. So batch processing being, I want to look at my entire cluster. I want to join. Yes, you can join. I want to do aggregations. And it will sit there and do all that stuff for you. So you can do some really, really complex stuff. And it's going to do it in memory. So not everyone here raised their hand about using Spark for production. One thing that's really exciting about Spark is that it's architected very, very fast. There are tests that show it being orders of magnitude faster than we do. So you also get fully distributed SQL. So if you really want to write out an SQL join, you can do it with Spark in your whole cluster. Now, this is analytical. This is not something that you're generally going to want to pass back in real time. Or if it is, it may be part of some reporting dashboard. We don't have an SLA of 10 milliseconds. So the way that all your data, is managed, and you have something called an RDD. It's called the Resilient Distributed Data Set. So RDDs, you can perform operations on them. You can perform a map, pass a function, and you get a result back, or you can do SQL queries. You can actually take an RDD and treat it as if it was a table in SQL. So you can just have really arbitrary sets of data. You can join RDDs from different sources to each other. So you can have, let's say, maybe you didn't figure out a way, where there is no way, to do the workload that you want. And you're like, I just need this absence component for this one small part of my app, but then I have the rest of my stuff in Cassandra. You can join MySQL to Cassandra using Spark. You can join from CSV files, and there's a million different sources. You can write your jobs in Scala, Python, or Java. Java off, I don't know why. You can use streaming. So streaming is really cool. You get these batches, and you get a chunk of data, and you get a bunch of data. You can do analytics on them. I've got a couple slides. I want to talk a little bit about what you can do with Spark streaming, how that works. And you've also got machine learning. This is good. I've got some really interesting, concrete examples of using machine learning libraries in Spark. Companies that are using some of this stuff, really, really fascinating. And then you can do graph analytics. So you can basically store a graph of data, and then you can traverse that graph using Spark. So what do we got here? What does Spark and Cassandra look like? Yes?
Yeah, I didn't understand the correlation. We're talking about Cassandra and Spark. I don't know what Spark is.
So that's what this slide looks like.
Okay.
All right. Spark basically works with Cassandra. So Spark is a platform for analyzing data, and you store your data in Cassandra. That's the dream setup. You've got super high availability and a platform that scales really well for doing data analysis.
Is it a wrapper around?
It's not a wrapper, but it's another application.
So where you process it, take snapshots of the data and it's just saying nodes and stores it in memories. Data processing. It's like MapReduce and stuff.
So one of the things that you want to do when you are running a Spark cluster is you've got, let's say, or a Cassandra cluster. So to talk to Spark, we're going to be using the open source connector that Datastax has released. And it basically allows you to, within a Spark job, you can talk to your Cassandra cluster, and you can pull the data out, and you can work on it as an RDD. You're going to be running your Spark nodes have one Spark node sitting on top of your Cassandra node, so one server has both applications. That way you get data locality, and it's really smart about what data it pulls out of Cassandra. It's going to do its best not to have to do a lot of network, invoke a lot of network overhead, because that's the last thing you want in a system that's supposed to be really fast. Ideally, you want to run 2 data centers. So I talked about how you can run Cassandra across 6 data centers. You want one of them for analytics. So it's going to be a fully replicated copy of the data set. And you run Spark over here. That way it doesn't interfere with the rest of your cluster. The last thing you want is to do some wild aggregation across 50 billion rows and have it interrupt the performance of your real-time system. And that's where we have, that's kind of where this Lambda architecture comes into play. I don't know if you guys are familiar with it, but the idea is you separate your batch stuff from your real-time stuff. And it allows you to effectively isolate any of the issues that will come about from your batch jobs. Because you may want to configure this differently, you may want to put bigger drives here or different drives, just totally different hardware, for whatever reason you want to do it. It's good to have everything separated out because it just mitigates the risk.
John, just one quick thing. If anyone needs validation, Sunny is about to leave. So you want to grab validation, please go ahead and do so with us.
I will.
Yeah. You want to
So the difference between Hadoop and Spark, I think that it's a few things. The in-memory thing is a part of it, but it's also it's an architectural rewritten from scratch that doesn't have a lot of legacy nonsense associated with it. And one of the big things about Hadoop that's really difficult for people to deal with is the number of is the size of the ecosystem. So there's like 100 different tools that do all the same thing, and to get good Hadoop performance, you have to know about like TEDs and it's complicated to set up a Hadoop cluster. And the jobs, you can have the canonical example of one count, and the Hadoop word count is like 65 lines of code. The Spark word count is like 5. Yeah, so you're talking about writing 10 of the code, which means 10 different bugs. Yes. It's compared to this, it looks awful. I would never let it do job here. I'll never write in my life. That's it. I would never. What I was going to say, I can affirmatively say I will never write a new job again in my entire life. Unless it was as an example to show how much I know.
So it's the same sort of operation, but it's
effectively. I mean, the functional constructs are all, like the idea of MapReduce is to break down almost any big data problem into MapReduce. Well, that's going to be a map. A joint is going to be translated into a map. If you can take you build a graph database in SQL database, all down the map.
some of the operation
Yes, it all translates into that. All right. Yeah. Good to go. All right. All right, I gotta pick this back up. I'm gonna get kicked out in just a minute.
Hey guys, can you keep going, please, comments going on? Thank you.
Yeah. All right. Here we go. So our use cases. The first question that came up was data migrations and what do we use Spark for? The question before came up over here, like what happens if we want to change the way we look at our data? We want to do a data migration. Traditionally, with the Cassandra world, this can be contained. You have to write your own like Java thing that moved a billion rows of data around and it took forever. You can do this with Spark. You can just create a new table and you can transform this table over to this table, and it's about like 8 lines of code. I have an example on my GitHub. It's really easy. You can do these same data migrations between databases. So the question was, what happens if I want to move from MySQL to Cassandra? You can take my MySQL tables, load them up as RDDs, and save them out into Cassandra. So this is a really, really easy way to do data migrations. So this is, oh, what do you know? I happen to have it on here. So this is, 23 lines of code, half of it spaces, and this is taking a single table in Cassandra and it's rewriting it in a new format. So the part that's really useful here is this one line. We have a user table that we pulled out as an RDD, and we map it to a new format, and then we save it as this food index RDD, and then we just call save to Cassandra, and it writes it out into the food to user index. So this is pretty straightforward. This was my first Spark job, and I was cackling like a maniac because it was so easy. This solved a really big problem because I had to move a billion rows around, and I've come up with some really creative ways to do it, and I don't have to be as creative anymore. I can just do this and it's done. So let's talk a minute about Spark SQL. I mentioned that you can register an RDD as a table. So that's what we have over here. We have our Cassandra table, comes from the text key space, person's table, and we just register as table, and you can arbitrary SQL process. You can do this with any RDD. So it's really, really fast. You can just the killer. This is the killer part. Yeah, this is amazing. You can do RDDs from different sources and join them together in SQL. Like, think about how amazing that is. So this system is so flexible. So we've got, next thing I'm going to talk about is streaming. So Spark streaming is really fun. What this does is it lets you get little batch windows into a stream of events. So you can do this with like 0FQ, you can do it with Kafka, you can have raw sockets. You're effectively just pumping data in, and it's going to sit there and go, here application, like here's a window of data, and it'll give you a list, right? And that list is an RDD. You can do aggregations across that list, you can process it. You can really do anything you want that you can do in any RDD. So one thing to keep in mind is that streaming is an approximation. You can end up with weird time slices on your windows. So if you're trying to build like an analytics engine and you need perfect answers, you're going to use this as an approximation and then use batch jobs later on to get your answers to perfect. So the way this window works, so this time right here, let's say I was doing a 1 second window. I have between time 1.1, 1.5, and 1.7. I have these 3 things that come in. And then in the next batch, I'm going to get these 3 things later. So no matter what comes in that window, you're going to have a batch. It's just going to be a list. I mean, it's boring, and that's good. Exciting can be bad. This is easy to use. I wrote my first streaming job. I wrote docs, took a couple hours, and all of a sudden I have this thing that's just working. So, yes?
1 second.
Yep. The question was, is the 1 second interval relative to the start time of the job? I believe so. Yeah. Well, this is actually going to be part of your application. So it's not a config because you write it out as code. You say, I know I want 1 second windows. Yes.
Slightly technical question. If we are storing time series in Cassandra, do they care about the time interval?
So so if you're storing time series in Cassandra, does this care about the time intervals? You're not generally going to be, you're not going to be getting data out of Cassandra. So typically the way that you would write your application is that you would store the raw data in Cassandra, and then you would put this is it queues a bunch of information coming in, and it uses whatever's in the queue, and it pulls everything on the front of the queue, and that becomes your batch. And then Cassandra is a terrible queue. So we don't use Cassandra incorrectly because it's like using a relational database with big data. It's just terrible. So we want to use something like Kafka if we have it stream processing or zero queue or we run our own socket implementation. What this is a distributed partition pub subsystem. So you can have as many subscribers you can have one publisher with 100 subscribers if you want. So this is really handy if, let's say, you have an analytics system and you want to stream real-time events back to somebody or back to dozens of people. You can have all, let's say, 24 people listening to one Kafka queue and pulling all that information out of it. You can also, let's say we have that same analytics system, you can be pumping events into this thing and then reading the data off into a Spark job, or Spark streaming job, perform the aggregations, and pump that data back into Kafka and get real-time results back to somebody in a second or two. So this is pretty cool. You can really have a live dashboard as to what's happening in your system in a completely real-time view with almost no work. I have a working demonstration of this. The product is called Killer Analytics, and the web UI is terrible, but it actually does work. So this massively scales. This architecture works very, very well. The only downside of it is that you need to use Zookeeper, which I'm not particularly wild about, but that's okay. So here is a streaming job. And this, I had to cut out some of this because I wanted it to fit on the slide. And you will be able to, actually this whole thing is available here in my Killer Analytics package. And what this does, you don't see like a while loop in here that indicates that the thing is happening over and over again. It kind of does that for you, so that was a little bit tricky for me to figure out at first. But what you have is an RDB coming in, and it's called raw events. And then, so this piece came over here, you have raw events. Call map, and then you do a bunch of stuff to it, and you call save Cassandra. And then basically we'll start up here again at the next batch. So it's just going to keep looping for you, and it's going to keep applying these maps and these transformations to your RDB, save it Cassandra, and you're good to go. Yes?
Can you compare it to Storm?
I can compare it to Storm. So Storm is more useful if you need the system to be not batches. So Storm, you can process each event individually. So it's really good if you want to do high frequency trading at a sub-millisecond level. This is more useful if you want to say, I want 1 second views of the world and perform batch operations on that. You can sort of do that with Storm. There's ways to do it, but setting it up is more complicated. Like this was not hard to set up. Storm was like very frustrating to set up. All right, I'm gonna just keep going. Do the time, okay? We got this guy. Things to keep in mind, right? As I mentioned, streaming is an approximation. So if you're really going to rely on this, if you're going to do any sort of financials with it, you only want to use streaming to get a rough approximation as to what's going on, and then go back and do batch jobs to make sure that the answers are accurate. I won't get into why. It took me a long time to figure this out. So yeah. And if we're going to use time series, one thing I didn't mention in Cassandra, I'll dig to your compaction to find that useful later on. We'll get into it now. Talk about machine learning a little bit. So, machine learning is really fun, right? We can do a whole bunch of stuff with it. The first thing I'm going to talk about is called clustering. Clustering is an example of unsupervised learning. And what we can do is we can figure out, effectively, we can say, I know that there are whatever number, I'm going to just say, divide everything into 4 groups. And what we have are all these data points. And what you get out of this is your machine learning algorithm, or in this case, it's 3, will intelligently figure out where your clusters are of things. So this is an example of figuring out the different types of flowers based on certain attributes that those flowers have. Because, it will be able to figure out what are the different categories of flowers, where are they, have a pretty good accuracy rate. And for this, we've got something called k-means clustering, and you give it, say, I want n number, divide by data into n number of clusters, and it will show you what you asked for. And you get this power iteration clustering, which is really nice if you want to cluster vertices with graph. Like, for instance, if you wanted to take a map and figure out where should I put, I want to open up 10 pizza restaurants, where should they go on the map? And you can figure out what the 10 best locations are within this graph, which happens to be a map. We've got logistic regression, which is really useful if you want to get a binary answer out of something. So if you want to say, predict the results of an election based on previous elections, you can then use logistic regression to pump in all your data and say, like, give me a prediction for this, yes or no, and it will give you an answer. And this is available in streaming, so you can get, you can keep pumping data in, and it will keep giving you answers to your questions. So it'll get better over time as well. Collaborative filtering. This one's really fun. This is how you build a recommendation. So if anyone here has a product catalog and users and some sort of either ratings or people are buying something, you can use the recommendation system through collaborative filtering to build whatever you want to suggest new products to your users. And this is a perfect match for Cassandra. This is like when people are buying stuff, that's time series. When people are rating stuff, that's time series. This sort of thing works really, really well. And as an example, a company that is using this is Spotify. So this is how Spotify does a lot of their recommendations, and they love it. And they are huge Cassandra users. They always present at the annual Cassandra conference, and it works really, really well for them. So it will probably work well for most of our applications. My setup's not as big as Spotify. Sorry. This is really important. It's really, really, like, everyone is going to walk out of here thinking, cool, I'm going to go ahead and deploy Cassandra and move all my applications over to it. That would be bad because there's probably a whole bunch of use cases where it's not the right case. For instance, do we have a data warehouse? If we have a data warehouse, Cassandra's not the right thing for you. If you've got a bunch of cold data and you want to query it like once a month, use something else. Throw it in HDFS. If you don't care about downtime, Cassandra might not be the right thing for you. If you don't need multi-DC, if you're really okay with running in one data center and having 6 hours of downtime, then Cassandra's probably the wrong thing. And that's okay. You know, the requirement is, do I have a lot of live data? Do I need uptime? Do I need multi-DC? If those are your requirements, then Cassandra's a great fit for you. And then Spark on top of that gives you great analytics. So when you're picking your distribution, you're trying to figure out what you're going to use with Cassandra, or which Cassandra version you're going to use. You've got two options. You can either roll open source, which is great, or open source guide. But you have to know, you are going to get the latest bleeding edge features. And support is going to come from Jira's mailing list, IRC. You may be the type of person that likes to fix your own bugs, or the type of person that just loves to dig through code and hack out things and add your own features. We need more of those people. If you are that type of person, come talk to me. I would love to help you out and get started on the open source side of things, because the more committers there are to Cassandra, the better. And if you want to go more of the enterprise route, where you get support integrated Spark, so you don't have to set it up yourself, it just comes installed. I haven't really talked about Solar for search, or integrated Solar as well. Certified Cassandra, a lot more QA, SLA, and their support. Datastax Enterprise is the way to go. We've got guys here that can tell you a lot more about it than I can. You can talk to Scott afterwards if you're interested in that. But what Datastax Enterprise gives you is a solution that you can deploy. You feel a little bit more comfortable with open source, and it's definitely good if you're, the enterprise guy that doesn't want to go alone. So that's no good to that's your question.
What's the free start?
Yeah, so the free starter program, we give Datastax Enterprise away to startups. That meets the criteria of less than $3 million in revenue and under $30 million in funding. So if you've got a company, you can run Datastax Enterprise.
Just make it like this.
Exactly. You can, yeah. Scott. So, yeah, that's my stuff. You guys have questions?
We've done that stuff.
Could you with Spark?
Maybe Spark versus Cassandra with Spark. Kind of the use case.
Wait, that wouldn't make.
HDFS.
Okay. If you're interested more in that data warehousing side of things, cold data, go to HDFS. The problem with going to the Hadoop world and HDFS, you can have downtime because it's not built for high availability. High availability is more of an afterthought. That's really the thing that differentiates it. Or you want super dense nodes. If you want to put 50, and that's the data warehouse. I want to put 50 terabytes of data per node, and I'm okay with a little bit of downtime. Roll out HDFS. You want it real time? Cassandra.
So you had this load Cassandra table with RDB.
Yes.
Right. So I'm new to Spark, so I just wanted to. It seemed like RDB is an object that is happening. That's like
Yes, so having a conversation going on. Please keep it on.
Thank you.
So I guess RDB is your wrapper, and underneath is your connector into Cassandra, and so it's like RDB API to word.
The question is, what is an RDD? I kind of brushed over it as a resilient distributed data set, but what you can think about it is a fully distributed list of data that's spread across your entire cluster. Whenever you do a query to Cassandra, you get the RDD, and it's, think of it, if you do a database query, you would typically get a list of results back. In this case, you get a list of results back that could potentially be spread across 100 machines. So you get to operate it on it as if it's a single list, but Spark transparently in the background is going to manage it across 100 machines for you.
So does that mean that when you say load this Cassandra table as an RDD, that by the time you get the RDD, all of the Cassandra table is loaded into memory on different nodes?
Exactly. The question was, is if you pull an RDD of a particular table, is it loading all of the Cassandra data in memory? Effectively, yes. Yes.
Just one more question.
Oh, okay, yeah.
Sorry, you mentioned that the stats goes to
Yes.
Is that like a really big project where it's going to have a proprietary database you're going to pull it into the
If the question is it a big project to write a connector? A Spark connector. It's hard for me to say because we take a lot of things into account with our connectors, so it's constantly being worked on by a full-time team. But if you had like a single machine and you wanted to talk to a Spark, it might not be as big of a problem. Now, Spark does support JDBC and ODBC, so if you can talk to that, you can go ahead. Okay. Yeah. So it looks like we're out of time. Okay. If anyone has any questions for me after, I'll be in the parking lot, I guess. or on Twitter, I am. Hold on, let me go back 45 slides. We can do this. Please don't kick me out. I'm Rusty Risley. I'll post the slides.
Yeah, look at the slides from Jon.
Yeah.
Before we leave, so we're going to wrap up the book, so we are going to just raise your hands and Jon will ask you a question for one of his slides.
Oh, I am.
Who will ask the question? Raise your hands, don't shout the answer.
Okay. Well, I pick one person?
Ask the question.
My man right here. What does RDD stand for? Boom! Someone just won a book.